We're in Chapter 12, Analysis of Variance, 12.1, One-Way Analysis of Variance, or Anova. We now extend the concept of comparing two population means from Section 9.2 to comparing three or more population means. The procedure for doing this is called Analysis of Variance, or Anova for short. Analysis of Variance, or Anova, is a method of testing the equality three or more population means. Anova is used with data categorized with one factor or treatment, so there is one characteristic used to separate the sample data into different categories. The analysis of variance, or Anova method, of the chapter requires the use of the F-distribution. Properties of the F-distribution. The F-distribution is not symmetric. It is skewed right. Values of the F-distribution are non-negative. And 3, the exact shape of the F-distribution depends on 2 different degrees of freedom. So you can look at the F-distribution in the diagram shown. So requirements to perform a one-way Anova test. First, there must be k simple random samples, one from each k population, or a random experiment with k treatments. 2, the k simple random samples must be independent of one another. That is, the subjects in one group cannot be related in any way to the subjects in the second group. 3, the population must be normally distributed. And then 4, the populations must have the same variance. That is, each treatment group has the population variance sigma squared. So next below it says, suppose that we are testing a hypothesis regarding k equal 3 population means. So we have, and so your null and your alternative hypotheses are going to be set up very similar to this. It's going to be different depending on the value of k. But h0 is going to be mu1 is equal to mu2 is equal to mu3. h1 is going to be at least 1. We've seen this wording before. Population mean is different from the others. And again, rewriting this in a way that it is relevant to the problem that we're dealing with. And also down below, you guys will notice that the mu's equal and mu's are not equal. So try to design an experiment that uses Anova with sample size of each treatment group being the same. They aren't always going to be the same, but it's a goal that we have. So example says the data in the table represents the number of corn plants in random sampled rows, a 17-foot by 5-inch strip for various types of plot. An agricultural researcher wants to know whether the mean number of plants for each plot type are equal. So first of all, you'll notice that we have 3 different plots here, 3 different plot types. And it also talks about the mean number of plants. So I know right now that we are dealing with mean, and I know that it is asking about more than 2. And so since we have more than 2, I know that we are going to be using Anova test. And so the first part on here says, find the null and the alternative hypotheses. So we're going to go ahead and write down H0. And H0 is going to be that the mean of first plot that we have is called the sludge plot, and I'm just going to go ahead and call that one SP. I'll call the other one SD for spring disc and NT for no-till. So the mean of SP is going to be equal to the mean for the spring disc, or SD, which is going to be equal to the mean of no-till, or NT. And then our alternative, H1, is going to start off with at least 1. And we are talking about the mean number of plants. So at least one mean is different than the others for the number of plants. So the next thing says, part B, It says state the requirements that must be satisfied to use the one-way ANOVA procedure. So the first thing that we have is that it needs to be a simple random sample. These are all listed on the previous page, and then they are all listed down here right below. So the first thing is that it has to come from a simple random sample. Second thing is that we have to have independent samples. So we have to have independent samples. The third thing that we have is that the populations must be normally distributed. And then for the last thing that we have to have is that the populations have the same variance. So all populations have same variance. So this is what we would have to check in order to conduct the Anova test. As at this point we don't have all that information written in the word problem, so we would have to be provided more information in order to go ahead and do this problem. Okay, that right below this, the box, give that a star, says steps for the Anova test with a TI 83 or 84 graphing calculator. Step 1 is to verify those requirements that we did right up above. Step 2 is deciding the level of significance alpha, which is normally given to you guys. Step 3 is determining your null and alternative hypotheses. And again, this depends on how many groups or categories that we do have. Also, underline the at least one, don't forget that. Step 4 is enter the observed data into L1, L2, L3, and so on. So the one that we had up above, there was 3 different groups, so we would be using L1, L2, and L3. And then we're going to go to stat test. We are using the Anova test. You are going to type in L1, L2, L3, and so on for the number of data sets, and then press enter. Calculate gives. It's going to give us the F, which is the test statistic, P, which is the p-value, and then we go through the testing just like how we've done so far this whole semester. So if the p-value is less than alpha, we reject the null, and then state your conclusion. Again, you always discuss H1, which is our alternative hypotheses. So the example that we have next, we're going to start. And this one says, a study was done to determine the average amount spent on textbooks per student is the same at Mount Sac, Chaffey College, Rio Hondo College, and Riverside Community College. What can be concluded at the 0.05 level of significance? And it says, assume that the population variances are the same. So for this one, we need to start off and we'll assume that the testing criteria has been met. You guys can check that on your own. But let's go ahead and write our null and our alternative hypotheses. So how do we know that we are using the Anova test? Well, I understand that that assumption that's written there is kind of a big indicator. The other thing too is that it's talking about the average amount that has been spent on textbooks, and average is another word that they like to use for mean. And so we're talking about the means, and there's more than just 2 sets of data. So we have 4 sets of data right now. We have Mount Sac, and I'm going to abbreviate that one MS. We have Chaffey College, CC, Rio Hondo College, RHC, and then Riverside Community College, so RCC. And so our null is going to be that these are all equal. So the mean amount of textbooks at Mount Sac would be equal to the mean amount at Chaffey College, which would be equal to the mean amount at Rio Hondo College, which would be equal to the mean amount at Riverside Community College. H1, our alternative hypotheses, is going to start off with at least 1. So at least 1. Mean amount. Spent on textbooks. per student is different than the others. So right now you're going to have to take all this information and we are going to have to enter these into L1, L2, L3, and L4. Again, checking to make sure you enter in those numbers correctly. We are going to go to Stat, go to Edit, and enter in our data into L1, L2, L3, and L4. And then once you have your data in there, we're going to go back into Stats, go over to Test, and we are going to use the Anova Test. And in the Anova Test, you need to list L1, L2, L3, and L4 because we have 4 sets of data in here. So second one, we'll put L1. You guys have a comma button. Second 2 for L2, comma. Second 3 for L3, comma. And then second 4 for L4. Close your parenthesis. Select enter. And you are going to get a test statistic along with a p-value. We found that the p-value is equal to 0.2297, and this is greater than alpha. Alpha was equal to 0.05 in this problem, and so this means that we do not reject H0. The next thing that we are going to have to do is to write our conclusion. So in conclusion, there is not sufficient evidence at the alpha equals 0.05 level of significance to conclude that at least one mean amount spent on textbooks per student is different than the others.